Lesson 4 in this unit is going to be on Charles's law and Gay-Lussac's law, two other gas laws. So we're going to talk about changing temperature of the gas, which refers to Charles's law. We're going to practice some problems, Gay-Lussac's law, and then practice more problems. If we increase the average kinetic energy, which again, we're increasing the temperature of a gas, the faster moving particles impact the walls of the container, which then create an increase of pressure. When you double the temperature, you're going to double the pressure. It's a direct relationship. So if you notice the picture on the right, you're going to see that the bottle, before it gets heated, is going to have a droopy balloon because the gas particles in the balloon are not moving as fast. Now on the balloon that is inflated, because it's above the heat, the water is causing the gas particles inside the balloon to heat up and increase in average kinetic energy, thus creating more impact on the walls of the balloon and inflating it. Think of a hot air balloon. This is how it works.
So again, as you increase pressure, your temperature is also going to increase as well, or if you increase your temperature, your pressure increases. Both of these are in a direct relationship, so a change to one of them is going to be an identical change to the other. Increasing of one will increase the other. A decrease in one will decrease the other.
So Charles's law, another gas law that we need to talk about, takes temperature and volume as the variables, while pressure and the number of moles are going to remain constant. As we said earlier, temperature and volume are directly related, so we're going to see a direct relationship in their changes as well.
So Charles's law, as Ms. Dematopoulos has said, is a relationship between temperature and volume. When you increase one, the other increases as well. We call this a direct proportionate. So therefore, as you increase the temperature, the gas molecules collide more often and have more energy. Due to this, gases expand and will occupy a larger volume. So if you think about blimps, like for example the Hindenburg, the entire body of the blimp is filled up with gas. How does this gas stay so big? Well, there has to be some sort of engine room that's supplying the heat that it needs for the gases to then flow and expand, creating the lift of the balloon. Again, Charles's law is a direct relationship between pressure and temperature, while Boyle's law from our previous video is an indirect relationship between volume and pressure. So this is Charles's law. V1 over T1 is equal to V2 over T2. You are doing division. Or, depending on what you're looking for, you are cross-multiplying each other. Again, your volumes must be the same unit. If V1 is liters and V2 is milliliters, you have to convert them because 1 liter is not the same thing as 1 milliliter. When you do your original and final temperatures, again, all gas law problems are going to be in Kelvin.
Why do they have to be in Kelvin?
Well, if you have standard temperature, which is 273 Kelvin, and you decided to put it down in Celsius, that means you're doing something over 0. In your calculator, do 5 over 0. See what happens.
So let's try a practice problem. A bike tire is filled with 2 liters of helium at 22 degrees Celsius and 760 millimeters of mercury. It is then placed outdoors on a hot summer day when the temperature is 31 degrees Celsius. If the pressure remains constant, what will the volume of the balloon be? So first thing we need to notice is that this is in Celsius. And again, these variables have to be changed into Kelvin before we can do anything. So using table T, you can see that Kelvin is equal to Celsius plus 273. So you take 273 plus 22 degrees, and you get 295 for the first temperature, and then you'll get 304 for the second temperature. Put all the variables into our formula, and you get 2 over 295 equals x over 304. You cross multiply and divide, and you end up with 304 times 2 divided by 295, which comes out to be 2.1 liters.
If you are increasing the temperature, as you see from 22 degrees Celsius to 31, you should also be increasing your volume because those gases need more space. If a balloon is filled with 5 liters of argon at 310 Kelvin at 1 atmosphere, the balloon is then placed in an oven where the temperature reaches 340 degrees Kelvin. So right off the bat, you're noticing we're increasing temperature. What is the new volume of the balloon if pressure was held constant? Thinking about this, you're increasing the temperature, so therefore your volume should increase as well.
Gay-Lussac's law is a little different. Instead of relating temperature to volume, we're going to now relate temperature to pressure, and those are going to be our variables. Now we're going to hold volume and the number of moles constant. As the temperature of a gas increases, the molecules have increasing kinetic energy, which means that they're moving faster. They're colliding with greater force, thus increasing the pressure. Again, another direct proportion.
So if you increase the temperature, you're going to become more pressurized. And if you decrease the temperature, you'll have less pressure. So again, thinking about that scenario, in both of these chambers you have the same amount of gas molecules. But in our first container, we're not heating it at all. So our temperature is going to be relatively low in comparison to the right, where we have a heater supplying lots of energy into our gas molecules. As the gases absorb that energy and they themselves move around faster and faster and faster, the pressure will be increasing inside the chamber on the right. Again, it's the same idea. As the temperature increases, the gas particles have greater kinetic energy, which is represented by the long arrows, and collisions are going to be more frequent and more forceful. This is why hot air tends to hurt. For example, if you're over a stove or over a grill or anything that gives off heat, that hot air, it's hitting you. You can feel it brush against you.
So we're going to try a sample problem. What is the pressure inside a 0.25 liter can of deodorant that starts at 25 degrees Celsius and 1.2 atmospheres if the temperature is raised to 100 degrees Celsius? Assume that volume was held constant throughout this.
Okay.
First thing we want to notice is that degrees Celsius has to be changed to Kelvin, again using table T's formula. So we get the first temperature to equal 298 Kelvin and the second temperature to equal 373 Kelvin. We apply these to the formula and we get 1.2 atmospheres over 298 is equal to X over 373. Manipulate the formula, get X by itself, and then finally find that it's 1.5 atmospheres. Again, does this make sense?
You're increasing the temperature, so therefore your pressure should increase as well.
So yes, it does.
All right, in this problem, we again have a container that's held at constant volume, and it's found to have a pressure of 364.7 kilopascals. Its temperature is 462 degrees Kelvin. It's got to be pretty hot. At what temperature will the container be when the pressure is reduced to 2.2 atmospheres? So right off the bat, we are noticing that our pressures are not in the same units. So the first thing we did is we converted the 2.2 atmospheres into kilopascals. Looking at the ratio, if 1 atmosphere is equal to 101.3 kilopascals, we can then take 2.2, multiply it by the kilopascal unit, and we'll get 222.86 kilopascals. This is our secondary pressure. Using the formula for Gay-Lussac's law, we plug in the variables that we know. Pressure over temperature is equal to pressure over temperature. We then get X by itself, and then we solve to get 282 degrees Kelvin. Again, does this make sense? You're noticing your kilopascals went from 364 to 222. A decrease in pressure must mean that you're becoming cooler. So going from 462 degrees Kelvin to 282 does make sense.